Let me give you another fractal that actually played an important role. It's contour set. Yet another puzzle, yet another paradox. Take all numbers between 0 and 1. How many numbers do you have? Infinite, right? What is the length of these numbers, the total length? 1. Now, let's take out the middle part. 0, 1/3, 2/3, 1. You still have infinitely many numbers, but the length got down by 2/3, right? So if I take another middle, and I can do it forever, right? What happens is that every time I do this, actually these points get immunity. We are perfectly sure that they will never get out of this set. So every time you do this, you decrease the length of the set by multiplying it by 2/3, but you also add twice more points that are going to remain there. Do you see? So at the end of the day, you have something called contour set, which has infinitely many numbers in it, but it's called Lebesgue measure. Its measure is 0. Its length is 0. So infinitely many points adding up to 0. Lebesgue? With S. This doesn't sound right.
You can check it.
We can check it. Let's check it. Yeah. Brilliant. Lebesgue measure of this is 0. All right. So what is the fractal dimension of this one? Self-similarity dimension. You are already pros in it. Right? So let me ask you, when I go from here to the next part, how many copies do I have?
2.
Very good. So I have 2 copies, 3 times the scaling, right? So ln 2 over ln 3 is something that is less than 1. So its dimension is less than 1 but more than 0. It's something in between points and lines. Okay? Now let me talk about something called, did I already write the title? No. So we are going to do something that is called chaos game. Okay, here's what we are going to do. We are going to have, let me start with red. Red dot, blue dot, and let's say green dot. We can start anywhere we want. Outside or inside, doesn't matter. We start somewhere, right? And then let's say these are, let's assign some numbers to them, 0, 1, and 2. So I'm going to throw a dice that has 3 sides, 0, 1, and 2. If it comes 0, I'm going to get halfway there. Make sense? Let's say another 0 came. So I go halfway there, okay? Let's say 2. I go halfway there. 1, I go halfway there. Another 1, I go halfway there. So we are going to play this game 1,000,000 times, and some pattern will emerge. And we will try to understand how that pattern emerges. Okay, chaos game. Let's see the code. So I'm picking between 1 and 3, 1, 2, 3, right? These are the coordinates of the 3 points, right? 0, 0, 0, 1, 1, 0, 0, 0, 1, 0, and 1/2 square root 3 over 2, right? Equilateral triangle. Then initialize starting point randomly, okay? And then the next one is depends on where you get the random number. So if it's R, do you realize that it's a translated code from MATLAB? It's quite obvious, right? Because it has 1, 2, 3s here. It has 1, 2, 3 minus 1s there. Yeah. So, but you go midway between the chosen point at random, right? And then you plot it. Okay, let's run it. Restart kernel. Okay, this is what you get. What is it? It's the Sierpinski triangle. Do you remember it? Now, why are we getting this? That's the question. Let's go back. And this is really the essence of fractal objects. It's a matter of taking a dough. Okay, I don't like the word dough because it sounds like duh. And is there a better word? What do you call these things that children play? Play-doh. Slime. Let's go with slime. You take a slime, you stretch it. Let's say Play-Doh. You put like green one and blue one. You fold it like this. You stretch it. You fold it. You stretch it. You fold it. You stretch it. What you are going to get is this intricate structure that will look like a contour set if you look from the side. If you cut it, it will actually look like a contour set. So what's going on here is that let me go to the end result. Let me go to the end result. If you take all the points of, let me not break this, let me make a copy. What happens to all points of Sierpinski triangle? Okay, all points. It's already there, let's say, the end result. What happens when we get 0? Imagine mapping all the points.
Then we halve it, and then we get to upper third of that.
Exactly. So it's basically mapped over here exactly. Do you buy it? Let me just show it again. So, okay. So let me think. Let's say this is just a triangle, just a triangle, not even a Sierpinski triangle, just a triangle. Okay. Let's see where the points go in this, on top of this. Like, where will this point go? It will go here, right? Where will this one go? It will go somewhere here, right? Where will this one go? It will go over here. Similar triangles, do you remember? Like if I have something like this and I'm taking this point over here halfway, so it has to go there, right? So all these are going to be mapped over here. All this thing is going to be mapped over here. All this thing is going to be mapped over here, right? So what happens is that the ultimate set, when you do the transformation, nothing changes. It's mapped to itself. because it has itself as a copy. Am I making sense? Yes? So if you did it with 4 points, for example, if you did it with 4 points, what would you get?
Again, we are halving the distance, right?
Yes.
In which case, something like a Sierpinski's square.
Mm-hmm.
I mean,
Would it still be empty in the inside? I'm not really sure
I am guessing
anymore.
it would be like a full square instead.
Full square, right? So we need to change something so that it doesn't get full square. So let me show you something. Let me show you some. I think we have to go 1/3
Yeah.
for the thing that I'm aiming for. Okay, what I'm aiming for is this Sierpinski carpet, where you remove the middle part, then you remove the middle parts from every point, okay? Then you remove the middle parts from here, etc. Okay. If we are aiming for that one, we shouldn't go to 1/2, we should go to 1/3, because we need to take this point all the way here. Does it make sense?
Yeah.
Should we risk writing this code?
Yes.
Okay. Okay. Let me risk. Write me a chaos game that gives Sierpinski carpet. Danke schön. Let's see if it will work. But this is Markdown? No worries. Let's make it Python. Ready? Okay. Couldn't do it. Should be ready on the first try. So let's change this. Let's change this code, okay? So I go from 1 to 5. Is that right? So this is 0, 1, 0, and 1, 1. 1, 1, and this is 3. We forgot the commas. And is it done? Should be done. Ooh. One coordinate is wrong. This is 0, 1. I expected a carpet. I got a wrong. 2/3?
Just multiply P of N of T Rn by 2. No, not like.
Anyways. Tell me.
Pn should be multiplied by 2, or T of Rn should be multiplied by 2.
Let's try.
It's high school game. Then the other one.
Let's try the other one. If it doesn't work, no worries. Your homework is to do it for a pentagon. So it's much more fun. Good luck with that. Okay. So now there is another way of finding the dimension, and I'm going to tell you. It's called pointwise correlation dimension. Alper, I thought that instead of breaking your heart, I should break my head. So I made a new code that zooms in Mandelbrot. Coming soon. Okay? You're welcome. So here is how this point-wise correlation works. You take a fractal, maybe a Sierpinski carpet or triangle, whatever. It's composed of points, right? So you land on one of those points and you start counting points around it. Okay? You have some radius r, let's say, and you increase this radius and see how the number of points changes as you change the radius. So if it's a two-dimensional object, what you expect is that as you increase the radius, the number of points exactly should be proportional to r squared, right? So this squared is the dimension. Do you buy it? Yes? And basically, we are going to do this procedure. We are going to plot it log r versus log n. And the slope is going to give us the dimension. Because over here, if you take the log of n, it's proportional to 2 times log of r, right? So the slope actually gives you the dimension. Good? Yes.
Instead, can you also do 1, 1, 2, 1, 2, 3, like for all lines you can write 1 and by summing them down.
Yeah. Of course, you don't do it once. Okay, you do it everywhere. Like you do it for this one, and you count the number of points. But maybe you are at some obscure point of the structure, so you do it many times. You sum up the points versus the radius in many different points, and then you average it out. Then you plot log n versus log r. Okay.
I have a question.
Sure.
What do we mean by the number of points?
We mean number of points within the circle, number of data points.
Usually, whenever we are at one dimension or two dimension, their cardinalities are the same.
Okay, this is a numerical procedure, so you have a finite number of points actually.
So we are randomly selecting points.
Yes, yes. And what we are going to do is as you have seen here, we have generated a Sierpinski triangle which has 100,000 points. Okay, so we are going to actually generate it again. This time we generated 200,000. Do you see it?
Yeah.
Then there is this pointwise correlation part. Let me start with this one. I wrote with D. Is that okay? Instead of R, it's D. Doesn't matter. It's a letter, right? So, look, I change D in the following fashion. I go from e to the minus 10 to e to the 1. Okay, linearly. So it's e to the minus 10, e to the minus 9, e to the minus 8. So I'm increasing the radius by starting from very small and increasing it exponentially. Then what this one is doing, this one is basically we keep the average number of points enclosed. Okay, if I use the first D, how many points on the average am I enclosing? Whether I sit there, etc. This is the number of points that were selected at random to average C. So we are going to do this procedure 1,000 times. Is it clear? So I choose 1,000 points at random. I go sit on them and do 10 different radii, count the numbers, average it out. Let's do it for this case. Okay. It first generates those 200,000 points. Okay. then it lands on here, there, over here, over here, over here, different places on the set, and increasing the radii. This is a typical curve that you are going to get, okay? We were expecting a line, right? We have a line in the middle side parts, but we also have these cutoffs. So what is happening here is that this larger cutoff is the cutoff of our structure, okay? What is the largest length that we have? When we reach there, we lose this linearity, okay? The other cutoff is the microscopic cutoff. I mean, if it was a perfect fractal, this would be a perfect line. But perfect fractals go on forever, both in microscopic direction and macroscopic direction. We have a finite thing. So what we are going to do is we are going to decide that, okay, over here, it seems to be linear. So let's repeat this one more time for that linear part. Instead of choosing minus 10 to 1, 11 points, let's choose minus 8 to 0. Actually, I was planning to do something over here to be on the safe side. What did I do? Minus 4.5 to 3.4. Is this a bad idea? Minus 4.5 is somewhere here. Minus 3.5 is somewhere. So I'm focusing here. So I'm going to run it one more time. This is generated fairly quickly, but the other thing needs to sum up the points. Okay. Okay. Do you see? We have a very nice line now. Now, we can get the fitting of this line. We can fit it into a polynomial. By the way, what was the dimension of this one?
Log 2 over log 3.
Log 3 over log 2.
Right.
Right? It's more than one dimension. Remember this? So we are going to compare this slope to that number log 3 over log 2. Do you see how close it gets? 1.589, 1.585. Okay? Good?
Yeah.
So these two things correspond to each other. So this is nice because we are going to get much more complicated fractals out of nowhere looking at nonlinear dynamical systems. And we will be able to figure out its dimension with this procedure. Now I want to talk to you about Julia set. Okay. Let's see Gaston Julia. We didn't even look at Mandelbrot, but this is the guy. Okay? He lost his nose in a war, in a battle. Okay. So what is Julia set? Not Conway. Julia. It's very, very similar to Mandelbrot set. It's so similar that I have to actually give you a comparison of what's going on. Okay? Okay, I need more space, so let me go here. Let's say this one is Mandelbrot. This one is Julia. Okay? in both cases, x and y, basically, in both cases, the points correspond to complex numbers, okay? But in Mandelbrot set, if you remember, the points were corresponding to C, right? We would choose some C, and we would do this z squared plus c, right? And so we would start with z equals to c, we would do z squared plus c, and if it's bounded, very good choice of words, bounded, then in the set, right? Very good. In Julia set, the points correspond to z, okay? And c is constant for the whole thing. C is just a number, 0.4 plus 0.5 I, let's say. Example, this is example. And then again, you do z squared plus c. If it's bounded, then it's, let me say, Mandelbrot set. This is Julia set. Very, very similar, right? So what are we expecting? So this one we already saw. As you can see, this one seems to be much more rich because you don't just get one picture, you get a picture for every number. So you change C, you will get a new Julia set. And it will be pretty as well, just like Mandelbrot set is. And here is our awesome code. Okay. So what do we have? 0.4 minus I times 0.4, some x mean, x maxes, mesh grade. Z starts with those values. If you remember before in the Mandelbrot, this was C equals to this. Okay. Now Z is equal to this. And the rest is just the same kind of a code. And if you run it, you get a pretty picture. So if you change this, like for example, plus, you are going to get another pretty picture. 0.6, you get this kind of a picture. 0.2, you get something like this, okay? But this way, looking at it this way is boring. Here comes the awesome code. Ready? Okay. So this is Mandelbrot set, right? And as we move our mouse, we are going to see the Julia sets corresponding to that C. Doesn't get any better than this. And you see the yellow dots? They are those loops. Like if you remember here, when you get closer to period 3, and now it's also starting with darker colors and gets brighter, so you can see which way it moves, right? So if I move here, it breaks into 3 points, and that corresponds to 3 lobes of the Julia set. And you can see that Julia set is mimicking Mandelbrot set. If you are in the darkness, it's dark. If you are over here, it's still dark. If you are in this, as you can see, over here we are actually, what do you call it? In a divergent place, right? That C is divergent, and as you can see, in those points, Julia set becomes disconnected. I hope I'm making sense. Am I? we can zoom. Ready? Yeah. It's working slower. Do you see, like it becomes 5? Let's go to this baby Mandelbrot over there. First of all, do you see this baby Mandelbrot a bit like that? So as you go here, period doubles, but we can't see it because the points are too close to each other. Let me reset it, and go to this baby Mandelbrot. Do you see that we have period 3 there? Yes? And if we zoom into that baby Mandelbrot, we are going to see okay, let's try it. If I go this way, do you see the doubling of the points?
Yes.
Yes? And if I go this way, do you see the tripling of the points?
Yes.
So you do understand, hopefully, why Mandelbrot has itself in it. Because it has this period 3 oscillation, right? But if you go to a certain point in it, it has period 3, but that period 3 within it, each one of those points split out exactly like the Mandelbrot splits out. Okay. Do you have anything you want to see here? Do you see, like, these parts are really nice?
Is it just me, or do these Julia sets sometimes look like dragons?
It's definitely not just you. Yes, indeed, they look like dragons or flowers. Like, yeah, okay, you can play with it at home, and hopefully it will work better in your computer while you are not recording and whatnot. Probably because if I don't record, I tried this at home and it was working much smoother. But this is enough, right? Okay. Julia set is easier to understand. So what we are going to do is we are going to go to this plan of this course. I forgot to open this web page beforehand. Do you have any questions in the meantime while Word is opening?
Is that physical usage of Julia set?
Hmm?
Is that physical usage of Julia set?
Are you going to make money?
Why not?
Very good question. So let me change it a little bit. Is there a physical fractal? Is there a fractal in nature? Yes, the trees are fractals, right?
No.
Okay. Yeah. What?
That's polymers.
Yeah, polymers are fractals. Okay. We have done all this. Okay. For example, we have already seen that. Look, this is a really fun image that is 17 megabytes. The image is 17 megabytes. What this is, it's Julia sets. Like, someone actually did a Julia set for every point, and you see this at the background. What was this guy with the mask? Hmm? Darth Vader at the background. Do you see the Julia sets? But I mean, if I didn't show you the thing, you would be much more surprised, of course, right? Yes.
Is it a Julia set made of Julia sets?
It's just plotting Julia sets at every point, and if you look it from far away, you see the Mandelbrot set lurking at the background. It is in the Dropbox. Let me, as I promised, understanding Julia set is easier. Oh, no.
What is the dimension of Mandelbrot, by the way?
What is your guess?
I don't have any. It should be greater than 1, but that's it.
I think it's 2. I think there's a boring result there, because its boundary is 2, and within it, it's 2. So, can you check it out? The internet, from the internet?
Do different Julia sets have same or different dimensions?
They have different dimensions, for sure. Coming soon. Okay. So here's what we are going to do. We are going to reverse engineer the Julia set. Okay? It's easier to reverse engineer Julia set because what is being mapped is these points themselves are being mapped. They are being stretched and like folded and stretched again, etc. Okay? Here, it's not the case. Here, every point corresponds to a different kind of stretching and mapping. But here, we are actually taking the space and stretching it out. Actually, transformation z squared corresponds to every point are being stretched away from the origin. It depends whether you have absolute value 1 greater or smaller than 1. Okay, so some of them shrink, some of them stretched out, and then you double the angle, because if z is r times e to the I theta, z squared is r squared times e to the 2I theta, or I 2 theta. Do you agree? So you basically stretch it, rotate it, then shift it, because you also do plus c, right? Very good. But ultimately, what remains within the set, if you remember, what remains within the set is this circle, right? Do you remember? That has the absolute value of 2. So we can start from the end point. So these points are going to remain, these points survived. They didn't diverge yet, right? Let's go backwards one step. So z goes to z squared plus c, right? Then if we want to go backwards, it corresponds to z goes to z minus c square root. Do you see it?
I do.
Yes? But plus and minus. Okay? So that's what we are going to do. We are going to start with this circle of radius 2, and we are going to subtract c. So I subtracted c, right? Then I take the square root. This is the square root. Oops. This is the square root because if you have something like this, okay, it spans, okay, so you have something like this, it spans the whole radius, right? Goes like to the whole radius. So you are going to halve those angles, right? Halving those angles means that everything will be basically stretched like this. But you have the plus part, also the minus part. That's why you have those two things. So let's watch it again. Boom. Boom. Yes? This was just one transformation. We went one step back. Now let's go one more step back. Shift it. Do the transformation, right? Shift it. Do the transformation. Shift it. Do the transformation. Shift it. Do the transformation. Until you get something, okay, something just like in the Sierpinski triangle. If we apply that stretching, it comes back to itself, right? This is going to come back to itself. Look, let's say this is the ultimate result. Shift it. No, we are not doing that. This is going forward, I guess. Okay, this is now just playing with us. But you get what I mean, right? Like if you took that final dragon, they are actually called dragons. If you take that dragon and shift it and do this, it will be the same thing. Okay? It will map to itself. How are we doing? Good? Yeah. Hopefully we understand fractals better. Blah, blah, blah. This is just showing in a much more fancy way how these Julia sets look like. Okay, this is a different Julia set. Maybe it's z to the 4 plus c. I don't know. Okay. Good? Good time for a break? Yes? Let's have a break.